I want you to meet my friends and Lucas, the instructors of this specialization.
Hi everyone.
Welcome to the specialization.
I've known Eunice for many years. He is an instructor at Stanford University and had also helped me create the deep learning specialization. Over the years, Eunice has taught hundreds of students learning AI and machine learning and NLP and other topics for the first time, and he's also mentored students on a huge variety of AI-related projects. So I'm really thrilled to have Eunice with us.
Thanks for the introduction, and it is always great working with you.
Lucas is a member of the Google Brain team where he does research on deep learning and NLP, so everything from machine translation to parsing. He is a co-author of Google's TensorFlow system, as well as of the Transformer network. And so his work has had a huge influence on all of NLP and AI. I'm really excited to also have Lucas as an instructor of this specialization.
Thanks for the introduction, Andrew.
Eunice and Lucas will walk you through the most important concepts in natural language processing. NLP has changed a lot over the last several decades. The field has started off using primarily rule-based systems where someone might code up a rule like, if you see the word good, then assume this is a positive customer review, to then using probabilistic systems that perform much better but still require a lot of hand engineering, to now where NLP relies much more on machine learning and deep learning.
More recently, with the rise of powerful computers, we can now train end-to-end systems that would have been impossible to train a few years ago. We can now capture more complicated patterns, and we can use these models in question answering, in chatbots, and in other applications.
Many of these applications are built with attention models, which you are going to learn in this specialization. A few years ago, these models would take weeks or even months to train, but with attention, you can train these models in just a few hours.
In this specialization, you learn to build NLP technologies, including the same technologies as what's deployed in many large commercial systems. In the first course, you learn about classification and vector spaces. Eunice, can you tell us a bit about the first course?
Sure. In course 1, you will learn to distinguish between pieces of text with positive sentiments and negative sentiments. You'll do so using logistic regression and naive Bayes classifiers. You'll also learn to represent words, queries, and documents, including other pieces of text, as numbers in vectors. You'll build your first machine translation system, and you'll learn about locality-sensitive hashing, which is just a method that will help you with efficient search.
Thanks, Eunice. After the first course, you then go on to the second course, in which you learn probabilistic models in NLP. So these are things like, given a few words, what is the probability of the next word being the word the versus of versus something else? So these are algorithms that all of us are maybe using almost every day. And in this specialization, you will learn how to build these algorithms yourself. After the first two courses, with the foundation that gives you, you then go on to the third course, which teaches you sequence models. And finally, in the fourth course, you learn about attention models, and this will take you up to state-of-the-art NLP models used for things like chatbots, question answering, and text summarization. Eunice, do you want to say a few words about that?
By the time you complete course 4, you'll be able to implement state-of-the-art neural machine translation, summarization, question answering, and chatbots. We will show you how you can combine attention and parallel computing to build these systems from the ground up. These models have high impact in industry. They could be used, for example, to automate call centers, or businesses can use them to make sense of large volumes of data.
I'm really excited for everyone to get started, to take these courses, learn these technologies, and to go build some great NLP systems.
Let's get started.
Awesome. See you in the classroom.
Let's jump in. Welcome to this first course of NLP, in which you learn about classification and vector spaces. You also learn about the application of these ideas to problems like sentiment analysis and word translation. For example, let's say you have 1,000 product reviews, so pieces of text written by users. Can you build a system to automatically go through all of these product reviews to figure out what fraction of them are positive reviews versus negative reviews. This course will teach you how. Lucas, can you say a few words about this first course?
Sure. In the first week, you'll learn how to represent text as a vector and build a classifier that will classify whether a sample text has a positive sentiment or a negative one. You will use logistic regression for that. In the second week, you'll use naive Bayes classifier on the same problem.
In the third week, you'll learn about vector space models. You'll learn how to represent text documents like tweets, articles, queries, or any object that contains a text as a vector. This is important in information retrieval, in indexing, in relevancy ranking, and also in information filtering. For example, when you look up a query online, the algorithm relies on all of these concepts to give you back your results. Finally, in week 4, you will build your first simple machine translation system, and you'll make use of locality-sensitive hashing to improve the performance of nearest neighbor search.
Thanks, Eunice and Lucas. So with that, let's get started and go on to the next video.
Welcome to the first week of Course 1. This week is all about logistic regression, which is a very important tool used in many applications in NLP. Logistic regression algorithms are particularly useful because they are easy to train and provide you with a good baseline result. This week, you'll use logistic regression for sentiment analysis of tweets. You'll first process your data, then you train your model, and finally you'll test the accuracy of your model. We've designed these courses so that each week I'll give you an overview of the material and Jonas will give you the details. So take it away, Jonas.
Okay, great. Follow me. Welcome. In this week, you're going to learn about supervised machine learning, and specifically, you're going to learn about logistic regression. In order for you to implement logistic regression, you need to take a few steps. In this video, you will learn about the steps required in order to implement this algorithm. So let's take a look.
In supervised machine learning, you have input features X and a set of labels Y. Now, to make sure you're getting the most accurate predictions based on your data, your goal is to minimize your error rate, or cost, as much as possible. And to do this, you're going to run your prediction function, which takes in parameters theta, to map your features to output labels Y hat. Now, the best mapping from features to labels is achieved when the difference between the expected values Y and the predicted values Y hat is minimized, which the cost function does by comparing how closely your output Y hat is to your label Y. Then you can update your parameters and repeat the whole process until your cost is minimized. So let's take a look at the supervised machine learning classification task of sentiment analysis. In this example, you have the tweet, let's say, I'm happy because I'm learning NLP. And the objective in this task is to predict whether a tweet has a positive or a negative sentiment. And you'll do this by starting with a training set where tweets with a positive sentiment have a label of 1, and the tweets with a negative sentiment have a label of 0. For this task, you'll be using your logistic regression classifier, which assigns its observations to 2 distinct classes. Next up, I'll show you how to do this. So to get started building a logistic regression classifier that's capable of predicting sentiments of an arbitrary tweet, you will first process the raw tweets in your training set and extract useful features. Then, you will train your logistic regression classifier while minimizing the cost. And finally, you'll be able to make your predictions.
So in this video, you learned about the steps required for you to classify a tweet. Given a tweet, you should classify it to either be positive or negative. In order for you to do so, you first have to extract the features, then you have to train your model, and then you have to classify the tweet based off your trained model. In the next video, you're going to learn how to extract these features. So let's take a look at how you can do that. Hello, welcome back. In this video, you're going to learn how to represent a text as a vector. And in order for you to do so, you first have to build a vocabulary, and that will allow you to encode any text or any tweet as an array of numbers. So let's dive in and see how you can do this.
Picture a list of tweets. Visually, it would look like this. Then your vocabulary V would be the list of unique words from your list of tweets. To get that list, you'll have to go through all the words from all your tweets and save every new word that appears in your search. So in this example, you'd have the word I, then the word am, and happy, because, and so forth. But note that the word I and the word am would not be repeated in the vocabulary. Let's take this tweet and extract features using your vocabulary. To do so, you'd have to check if every word from your vocabulary appears in the tweet. If it does, like in the case of the word I, you would assign a value of 1 to that feature, like this. If it doesn't appear, you'd assign a value of 0, like that. And in this example, the representation of your tweet would have 6 ones and many zeros, and these correspond to every unique word from your vocabulary that isn't in the tweet. Now, this type of representation, with a small relative number of non-zero values, is called a sparse representation. Now, let's take a closer look at this representation of this tweet. In the last slides, I walked you through extracting features to represent this tweet based on a vocabulary, and I arrived at this vector. This representation would have a number of features equal to the size of your entire vocabulary, and it would have a lot of features equal to 0 for every tweet. With this sparse representation, a logistic regression model would have to learn n plus 1 parameters, where n would be equal to the size of your vocabulary, and you can imagine that for large vocabulary sizes, this would be problematic. It would take an excessive amount of time to train your model, and much more time than necessary to make predictions.
Given a text, you learned how to represent this text as a vector of dimension v. Specifically, you did this for a tweet, and you were able to build a vocabulary of dimension v. Now, as v gets larger and larger, you'll face certain problems. In the next video, you will learn to identify these problems. You will now learn to generate counts, which you can then use as features into your logistic regression classifier. Specifically, given a word, you want to keep track of the number of times that word shows up in the positive class. And given another word, you want to keep track of the number of times that word showed up in the negative class. Using both those counts, you can then extract features and use those features into your logistic regression classifier. So let's take a look at how you can do that.
It is helpful to first imagine how these two classes would look. Here, for instance, you could have a corpus consisting of 4 tweets, and associated with that corpus, you would have a set of unique words, your vocabulary. In this example, your vocabulary would have 8 unique words. For this particular example of sentiment analysis, you have 2 classes. One class associated with positive sentiment, and the other with negative sentiment. So taking your corpus, you would have a set of 2 tweets that belong to the positive class, and a set of 2 tweets that belong to the negative class. Let's take the set of positive tweets. Now take a look at your vocabulary. To get the positive frequency of any word in your vocabulary, you'll have to count the times that it appears in the positive tweets. For instance, the word happy appears 1 time in the first positive tweet, and another time in the second positive tweet. So its positive frequency is 2. The complete table looks like this. Feel free to take a pause and check any of its entries. The same logic applies for getting the negative frequency. However, for the sake of clarity, look at an example. The word am appears 2 times in the first tweet, and another time in the second one. So its negative frequency is 3. Take a look at the entire table of negative frequencies and feel free to check its values. So this is the entire table with the positive and negative frequencies for your corpus. In practice, when coding, this table is a dictionary mapping from a word class, pair, to its frequency. So it maps the word and its corresponding class to the frequency, or the number of times that word showed up in the class.
You now know how to create a frequency dictionary, which maps a word and the class to the number of times that word showed up in the corresponding class. In the next video, you're going to use your frequency dictionary to represent a tweet. Welcome back. You previously learned to encode a tweet as a vector of dimension v. You will now learn to encode a tweet, or specifically represent it, as a vector of dimension 3. In doing so, you'll have a much faster speed for your logistic regression classifier, because instead of learning V features, you only have to learn 3 features. Let's take a look at how you can do this.
You just saw that the frequency of a word in a class is simply the number of times that the word appears on the set of tweets belonging to that class, and that this table is basically a dictionary mapping from word class pairs to frequencies, or it just tells us how many times each word showed up in its corresponding class. Now that you've built your frequencies dictionary, you can use it to extract useful features for sentiment analysis. What does a feature look like? Let's look at the arbitrary tweet M. The first feature would be a bias unit equal to 1. The second is the sum of the positive frequencies for every unique word on tweet M. And the third is the sum of negative frequencies for every unique word on the tweet. So to extract the features for this representation, you'd only have to sum frequencies of words. Easy, right? For instance, take the following tweet. Now, let's look at the frequencies for the positive class from the last lecture. The only words from the vocabulary that don't appear on this tweet are happy and because. Now let's take a look at the second feature from the representation that you saw on the last slide. To get this value, you'll need to sum the frequencies of the words from the vocabulary that appear on the tweet. At the end, you'll get a value equal to 8. Now let's get the value of the third feature. It is the sum of negative frequencies of the words from the vocabulary that appear on the tweet. For this example, you should get 11 after summing up the underlined frequencies. So for this tweet, this representation would be equal to the vector 1, 8, 11.
You now know how to represent a tweet as a vector of dimension 3. In the next video, you will learn to pre-process your tweet, and as a result, you will use those pre-processed words as words of your vocabulary. Hello. You'll now learn about 2 major concepts of pre-processing. The first thing you'll learn about is called stemming, and the second thing you will learn about is called stop words. And specifically, you will learn how to use stemming and stop words to pre-process your text. Let's take a look at how you can do this.
Let's process this tweet. First, I remove all the words that don't add significant meaning to the tweet, aka stop words, and punctuation marks. In practice, you would have to compare your tweet against 2 lists, one with stop words in English and another with punctuation. These lists are usually much larger, but for the purpose of this example, they will do just fine. Every word from the tweet that also appears on the lists of stop words should be eliminated. So you'd have to eliminate the word and, the word are, the word a, and the word at. The tweet without stop words looks like this. Note that the overall meaning of the sentence could be inferred without any effort. Now let's eliminate every punctuation mark. In this example, there are only exclamation points. The tweet without stop words and punctuation looks like this. However, note that in some contexts, you won't have to eliminate punctuation. So you should think carefully about whether punctuation adds important information to your specific NLP task, or not. Tweets and other types of texts often have handles and URLs, but these don't add any value for the task of sentiment analysis. Let's eliminate these 2 handles and this URL. At the end of this process, the resulting tweet contains all the important information related to its sentiment. Tuning Great AI Model is clearly a positive tweet, and a sufficiently good model should be able to classify it. Now that the tweet from the example has only the necessary information, I will perform stemming for every word. Stemming in NLP is simply transforming any word to its base stem, which you could define as the sets of characters that are used to construct the word and its derivatives. Let's take the first word from the example. Its stem is ton, because adding the letter E, it forms the word tune. Adding the suffix ed forms the word tuned, and adding the suffix ing, it forms the word tuning. After you perform stemming on your corpus, the words tune, tuned, and tuning will be reduced to the stem ton, So your vocabulary would be significantly reduced when you perform this process for every word in the corpus. To reduce your vocabulary even further, without losing valuable information, you'd have to lowercase every one of your words. So the word great, great, and great would be treated as the same exact word. So this is the final preprocessed tweet as a list of words.
Now that you're familiar with stemming and stop words, you know the basics of text processing. In the next video, you can use your process tweets function to extract a matrix X, which represents all the tweets in your dataset. You will now use everything that you learned to create a matrix that corresponds to all the features of your training example. Specifically, I will walk you through an algorithm that allows you to generate this X matrix. Let's take a look at how you can build it.
Previously, you saw how to preprocess a tweet like this one to get a list of words that contain all the relevant information for the sentiment analysis task in NLP. With that list of words, you would be able to get a nice representation using a frequency dictionary mapping, and finally, get a vector with a bias unit and 2 additional features that store the sum of the number of times that every word on your processed tweets appear in positive tweets, and the sum of the number of times they appear in negative ones. In practice, you would have to perform this process on a set of M tweets. So given a set of multiple raw tweets, you would have to pre-process them one by one to get a set of lists of words, one for each of your tweets. And finally, you'd be able to extract features using a frequencies dictionary mapping. At the end, you'd have a matrix X with M rows and 3 columns, where every row would contain the features for each one of your tweets. The general implementation of this process is rather easy. First, you build the frequencies dictionary, then initialize the matrix X to match your number of tweets. After that, you'll want to go over through your sets of tweets carefully, deleting stop words, stemming, deleting URLs and handles, and lowercasing. And finally, extract the features by summing up the positive and negative frequencies of the tweet. For this week's assignment, you've been provided some helper functions, build freaks and process tweets. However, you'll have to implement the function to extract the features of a single tweet.
That was a lot of code, but at least now you have your X matrix. And in the next video, we'll show you how you can feed in that X matrix into your logistic regression classifier. Let's take a look at how you can do that. You will now get an overview of logistic regression. Previously, you learned to extract features, and now you will use those extracted features to predict whether a tweet has a positive sentiment or a negative sentiment. Logistic regression makes use of a sigmoid function, which outputs a probability between 0 and 1. Let's take a look at the overview of logistic regression.
Just a quick recap. In supervised machine learning, you have input features and a set of labels. To make predictions based on your data, you use a function with some parameters to map your features to output labels. To get an optimum mapping from your features to labels, you minimize a cost function which works by comparing how closely your outputs y hat is to the true labels y from your data, after which the parameters are updated and you repeat the process until your cost is minimized. For logistic regression, this function, f, is equal to the sigmoid function. The function used to classify in logistic regression, h, is the sigmoid function. And it depends on the parameters theta and in the features vector x superscript I, where I is used to denote the ith observation or data point. In the context of tweets, just the ith tweet. Visually, the sigmoid function has this form, and it approaches 0 as the dot product of theta transpose x over here approaches minus infinity, and 1 as it approaches infinity. For classification, a threshold is needed. Usually, it is set to be 0.5, and this value corresponds to a dot product between theta transpose and x equal to 0. So whenever the dot product is greater or equal than 0, the prediction is positive. And whenever the dot product is less than 0, the prediction is negative. So let's look at an example in the now familiar context of tweets and sentiment analysis. Look at the following tweet. After pre-processing, you should end up with a list like this. Note that handles are deleted, everything is in lowercase, and the word tuning is reduced to its stem, ton. Then, you would be able to extract features given a frequencies dictionary and arrive at a vector similar to the following, with a bias unit over here, and two features that are the sum of positive and negative frequencies of all the words in your processed tweet. Now, assuming that you already have an optimum set of parameters, theta, you would be able to get the value of the sigmoid function, in this case equal to 4.92, and finally, predict a positive sentiment.
Now that you know the notation for logistic regression, you can use it to train a weight vector theta. In the next video, you will learn about the mechanics behind training such a logistic regression classifier. In the previous video, you learned how to classify whether a tweet has a positive sentiment or a negative sentiment using a theta that I have given you. In this video, you will learn your own theta from scratch, and specifically, I'll walk you through an algorithm that allows you to get your theta variable. Let's see how you can do this.
To train your logistic regression classifier, iterate until you find a set of parameters, theta, that minimizes your cost function. Let us suppose that your loss only depends on the parameters theta1 and theta2. You would have a cost function that looks like this contour plot on the left. On the right, you can see the evolution of the cost function as you iterate. First, you would have to initialize your parameters theta. Then, you will update your theta in the direction of the gradient of your cost function. After 100 iterations, you would be at this point. After 200, here, and so on. After many iterations, you would arrive to a point near your optimum cost, and you'd end your training here. Let's look at this process in more detail. First, you would have to initialize your parameters vector theta. Then, you'd use the logistic function to get values for each of your observations. After that, you'd be able to calculate the gradient of your cost function and update your parameters. Finally, you'd be able to compute your cost j and determine if more iterations are needed according to a stop parameter or maximum number of iterations. As you might have seen in the other courses, this algorithm is known as gradient descent.
Now that you have your theta variable, you want to evaluate your theta, meaning you want to evaluate your classifier. Once you put in your theta into your sigmoid function, do you get a good classifier or do you get a bad classifier? In the next video, we will show you how you can do this. Now that you have your theta, you will use this theta to predict on new data points. For example, given a new tweet, you will use this theta to say whether this tweet is positive or negative. In doing so, you want to analyze whether your model generalizes well or not. In this video, we will show you whether your model generalizes well or not, and specifically, we'll show you how to compute the accuracy of your model. Let's take a look at how you can do this.
For this, you will need xval and yval, data that was set aside during trainings, also known as the validation set, and theta, the set of optimum parameters that you got from training on your data. First, you will compute the sigmoid function for xval with parameters theta. Then, you will evaluate if each value of h of theta is greater than or equal to a threshold value, often set to 0.5. For example, if your hx theta is equal to the following vector, 0.3, 0.8, 0.5, etc., up to the number of examples from your validation set, you're going to assert if each of its components is greater than or equal to 0.5. So is 0.3 greater than or equal to 0.5? No. So our first prediction is equal to 0. Is 0.8 greater than or equal to 0.5? Yes. So our prediction for the second example is 1. Is 0.5 greater than or equal to 0.5? Yes. So our third prediction is equal to 1, and so on. At the end, you'll have a vector populated with zeros and ones indicating predicted negative and positive examples, respectively. After building the predictions vector, you can compute the accuracy of your model over the validation set. To do so, you will compare the predictions you have made with the true value for each observation from your validation data. If the values are equal and your prediction is correct, you'll get a value of 1 and 0 otherwise. For instance, if your prediction was correct, like in this case where your prediction and your label are both equal to 0, your vector will have a value equal to 1 in the first position. Conversely, if your second prediction wasn't correct, because your prediction and label disagree, your vector will have a value of 0 in the second position, and so on and so forth. After you have compared the values of every prediction with the true labels of your validation set, you can get the total times that your predictions were correct by summing up the vector of the comparisons. Finally, you'll divide that number over the total number m of observations from your validation set. This metric gives an estimate of the times that your logistic regression will correctly work on unseen data. So if your accuracy is equal to 0.5, it means that 50% of the time your model is expected to work well. For instance, if your y-val and prediction vectors for 5 observations look like this, you'll compare each of their values and determine whether they match or not. After that, you'll have the following vector, with a single 0 in the third position, where the prediction and the label disagree. Next, you have to sum the number of times that your predictions were right and divide that number by the total number of observations in your validation set. For example, you get an accuracy equal to 80%.
Congratulations on finishing the first week of this specialization. You learned many concepts this week. The first thing you learned is you learned how to pre-process a text. You learned how to extract features from that text. You learned how to use those extracted features and train a model using those. Then you learned how to test your model. In this week's programming exercise, you're going to get a chance to implement all these concepts that we spoke about. Feel free to go ahead and do the programming exercise. There's also an optional video at the end of this week which covers the intuition behind the cost function for logistic regression. If you don't want to watch that video, feel free to go to next week, where you will learn about a new classification algorithm known as naive Bayes. Good to see you again. In this optional video, you're going to learn about the intuition behind the logistic regression cost function. Specifically, you will understand why the cost function is designed that way. You'll see what happens when you predict the true label, and you'll see what happens when you predict the wrong label. Let's dive in and see how this logistic regression cost function is designed.
Let's have a look now at the equation of the cost function. While this might look like a big complicated equation, it's actually rather straightforward once you break it down into its components. First, have a look at the left-hand side of the equation where you find a sum over the variable m, which is just the number of training examples in your training set. This indicates that you're going to sum over the costs of each training example. Out front, there is a minus 1 over m, indicating that when combined with the sum, this will be some kind of average. The minus sign ensures that your overall cost will always be a positive number, as you'll see clearly later in this video. Inside the square brackets, the equation has two terms that are added together. To consider what each of these terms contribute to the cost function for each training example, let's have a look at each of them separately. The term on the left is the product of y superscript I, which is the label for each training example, multiplied by the log of the prediction, which is the logistic regression function applied to each training example, represented as h of superscript I and a parameter theta. Now, consider the case when your label is 0. In this case, the function h can return any value, and the entire term will be 0 because 0 times anything is just 0. What about the case when your label is 1? If your prediction is close to 1, then the log of your prediction will be close to 0 because, as you may recall, the log of 1 is 0. And the product will also be near 0. If your label is 1 and your prediction is close to 0, then this term blows up and approaches negative infinity. Intuitively, Now you can see that this is the relevant term in your cost function when your label is 1. When your prediction is close to the label value, the loss is small. And when your label and prediction disagree, the overall cost goes up. Now consider the term on the right-hand side of the cost function equation. In this case, if your label is 1, then the 1 minus y term goes to 0, and so any value returned by the logistic regression function will result in a 0 for the entire term. Because again, 0 times anything is just 0. If your label is 0 and the logistic regression function returns a value close to 0, then the product in this term will again be close to 0. If, on the other hand, your label is 0 and your prediction is close to 1, then the log term will blow up and the overall term will approach to negative infinity. From this exercise, you can see now that there is one term in the cost function that is relevant when your label is 0, and another that is relevant when the label is 1. In each of these terms, you're taking the log of a value between 0 and 1, which will always return a negative number, and so the minus sign out front ensures that the overall cost will always be a positive number. Now let's have a look at what the cost function looks like for each of the labels, 0 and 1, over all possible prediction values. First, we're going to look at the loss when the label is 1. In this plot, you have your prediction value on the horizontal axis and the cost associated with a single training example on the vertical axis. In this case, j of theta simplifies to just negative log h x of theta. When your prediction is close to 1, the loss is close to 0, because your prediction agrees well with the label. And when the prediction is close to 0, the loss approaches infinity, because your prediction and the label disagree strongly. The opposite is true when the label is 0. In this case, j of theta reduces to just minus log 1 minus h of x theta. Now when your prediction is close to 0, the loss is also close to 0. And when your prediction is close to 1, the loss approaches infinity.
You now understand how the logistic regression cost function works. You saw what's happened when you predicted a 1 and the true label was a 1. You also saw what's happened when you predicted a 0 and the true label was a 0. In the next week, you will learn about naive Bayes, which is a different type of classification algorithm which also allows you to predict whether a tweet is positive or negative.
Great job getting through the first week of Course 1. You now know how to train a logistic regression classifier. In this week's programming assignment, you'll be preparing text data and building, training, and testing your own logistic regression model. It's really exciting. We created a quiz at the end that contains some of the questions you might be asked in an interview about these topics. Next week, you'll explore another NLP classification method called naive Bayes. Good luck with the programming assignment.
Good luck!